Hello, my audible? Your video just froze.
Yes, you're
Yeah, you're
audible.
right.
Okay, hello everyone. So like today's talk is about some applications of linear algebra in some combinatorics problems. So in most of the problems, like we'll see like the statement will not have anything to suggest linear algebra model straight away, but we'll try to sort of use some stuff. We'll try to develop some sort of a framework for some related-ish problems. And so I'm assuming everyone here knows like what like dimension of a vector space means and what linearly independent means. I'll just mention anyways. So like suppose you have some vectors v1 up till vn in a vector space. Am I audible now?
Yep.
Hello?
Yeah.
Okay. So just tell me when I am not audible or something. Also, like if you guys have any questions, please like unmute yourselves and ask, or you can even drop it in the chat. So they are called linearly independent if there does not exist constants Ci such that summation Ci Vi equal to 0 and not all Ci equals 0. So in other words, if you have like a bunch of linearly independent vectors, then if you have some linear combination of them summing to 0, then you can actually say that all the constants are 0. So let us look at a problem first. So consider a town of n citizens, which which form m clubs with following rules. So first is every club has odd number members, and the number of common members between any two clubs is even. So that's a problem statement. So prove that m is at most n. So yeah, so is the problem statement clear to everyone? So we have like a town of, so we are sort of, you can think of the citizens as like like numbers from 1 to n, and the clubs as sort of sets. Then we are looking at a family of sets C1, C2 up till Cm, which each of them are the clubs, such that every Ci is like has odd cardinality, and the size of Ci intersection Cj is always even. So here's what we are going to do, sort of. So this is sort of a very standard thing. So what we are going to do is like we will think of sets of subsets of 1, 2 up till n as vectors in 0, 1 power n. So this is basically called f to n. So this is basically like you have n coordinates and you have a 0 or a 1 in every coordinate. So suppose I have like a subset is like, suppose my n is 5 and I have a subset of the form 1, 3, 4. Then my corresponding vector is like 1, 0, 0. No, sorry, not 0 here. A 1 here, a 1 here, and a 0. So basically, because I'm avoiding 2 and because I'm avoiding 5, you put a 0 in those locations. So in this way, you can think of subsets as this question. So this way you can think of subsets as like vectors in F to N. So we say F2 because like obviously 0 and 1. So now the idea is like, so let Vi denote the corresponding vector for.
We have that dot product is always even, right?
Yeah, for not, yeah, that is one thing. And what else can you say about like just the Vi themselves? Like use okay,
Like
I'm
product
using
with
the
itself,
expression which is
it's
like
odd.
below. Vector for Vj. Yeah, so the idea is like, so now we are given that that is correct. So we are given that the size of every club is odd. So this sort of translates to saying Vi dotted with itself will give you a 1. So what does that mean? So like when you suppose you have like an odd number of elements, an odd number of elements means an odd number of ones in itself, right? So when you dot it with itself, you will get like, you will get like common number of ones. So think about this like this: dotting gives a common number of ones mod 2. So so this basically says that Vi dot Vi will give me 1, and Vi dot Vj, which is basically intersection Ci Cj mod 2, is going to be 0 for all I not equal to j. So now I know that I have m vectors Vi, right? And I want to prove that m is at most n. So what I'm going to actually claim something stronger, I will say that I will prove that these vectors are actually linearly independent. So this would obviously prove m at most n, because in F2n you can have only n linearly independent guys, right? So we prove the VIs are linearly independent. So assume not, then there will exist some constants Ci in 0 or 1, such that summation Ci Vi equals to 0, and wait, sorry, Ci do not. So there will exist constants such that Ci Vi equal to 0, and not all Ci equal to 0. So now the trick is basically we will dot both sides. So now the trick is basically we are going to dot both sides with like Vi one at a time. So suppose, so call this equation start. So consider start times, so start dot with like, so basically consider the equation start and dot both LHS and RHS with Vi. So that would give you summation Ci times Vk dot Vi, well, like the index runs from K to M, let's say, and Vi, the I index is fixed, equals to 0. But then you know that Vk dot Vi is equal to 0 for K not equal to I. So the only non-zero value is, we get it from I equals, so from K equals I. So that is like the only non-zero value is Ci times Vi dot Vi, which is just 1, right? And the 0 still remains. So this means that Ci equals to 0. But since I was arbitrary, this concludes. Arbitrary, this shows that Ci equal to 0 for all I. So this implies linear independence. So any questions with this proof? So what we did was like we sort of interpreted the question and we interpreted the subsets as like elements in F to N. We realized that like the dot product itself is always 1. The dot product with anything else is always 0. And now we sort of claimed something stronger, that's like the VIs are actually linearly independent. If not, then you would find some linear combination with summing to 0, and then you dot it with some vector Vi, like one at a time, and then you'd get like the individual constant for Vi, the Ci is equal to 0, which, and since I was arbitrary, you sort of conclude that this is linearly independent. So now to sort of the construction for this, so like construction for m equals to n is very easy. You just take every member to be in a club of their own. Construction is just like you take the ci to be just I. So everyone has set has like size 1, and the intersection is always 0, which is 0. So we are fine. So now there are a lot of sort of variations of this problem. You can do the problem for when mod ci is even, mod cj
I
is
had a
so
doubt.
you can do the problem. Yeah, go ahead.
How does linear independence finish?
So I know that like I have some number of linearly independent vectors, right?
Yeah.
So, but I also know that like you cannot have more than n independent vectors in f to n, right? Because the dimension of the vector space is n.
Okay, fine. Yeah.
Right. So now there are sort of variations of this problem. So variations are, one variation says, suppose ci is even and ci intersection cj is odd, then what's the number? Then another one says, suppose ci is even and ci intersection cj is odd. And the last one says both of them are odd. So as it turns out, this case is very hard to solve. So this is hard. So I'll not go over the proof of this. This will require a bit more advanced linear algebra, but like do feel free to like read about this. The proof is quite interesting. So what I will do is I will talk about this case, and this can be a sort of an exercise. It's not very hard to determine it from the previous cases. So new problem. So the previous problem we encountered is called the odd town problem. So new problem is suppose mod ci is even.
Aren't 1 and 2 same?
ci. Oh, did I just? Oh, sorry. I was supposed to write even here. Sorry.
Yeah.
Sorry.
Okay.
Yeah. So the new problem is the sizes of all these clubs are even and the intersection is odd. So what do you think the bounds will be? So there are, let's say, m clubs. So bounds on n. So can someone tell me a construction? So if you're trying to construct something like, maybe like, let's say, start with the most basic sort of, you need CIs to be even. So you need at least 2 elements in every one of them. So maybe just start something with like, if all of your CIs were like 2 element sets, and what's the best that you can do?
Like for 3 elements, you can get 1, 2, 1, 3, and 2, 3. So like you can at least get n clubs.
Okay.
But that seems too less.
And 1, 3. Okay. And for maybe let's say 4, what can you do?
1, 2, 1, 3, 1.
1, 3 and 1, 4.
Yeah. But okay.
And
I think you can also do
more?
1, 2, 2, 3, 3, 4, and 4, 1. No, that won't work. You only get 3.
Yeah.
4.
So right. So does that give you an idea of the like what the actual answer, like what the bound should look like? So for 3, we found like when n equals 3, then m is at most 3. When n equals 4, m is also at most 3. Then for what can you say about n equals 5? If 5. Oops.
We can always do 1, 2, 1, 3, 1, 4, 1, 5.
1, 2, 1, 3, 1, 4, 1, 5. Okay, that gives me 4. Can you do any better?
Oh
So
yeah,
can
just
I
add 2,
add in?
3, 4, 5.
Right. So that gives me for n equals 5, you get 5, right? So this is 3, this is uh, 3, and for n equals 5, you get 5. So does that give, so maybe let's do another case for n equals 6 to maybe just sort of highlight what the bound should be.
So
For
like
n
for
equals,
n odd, we have n, and for n even, we have n minus 1.
right, that's the idea. So for n equals to 6, again, we can sort of do something like 1, 3, 1, 4, 1, 5, and 1, 6. That's 5 guys, right? So I'll just write the construction on the next page. So construction is for n odd, sorry, for n even, let's do first. So for n even, it's 1, 2, 1, 3, up till 1 n. So these are n minus 1 guys. And for n odd, also add in 2, 3, 4, up till n. So that's n sets, right? So now so this is a bit of a harder problem than the previous one. So I sort of want to prove that. So let's try to do the case n even first. So I want to prove m is at most n minus 1. So yeah, so again, let vi denote vector for ci. So what can we do? What are the dot product conditions in this case?
Vi dot Vi is 0. Vi dot Vj
Right.
is for I not equal to j.
Right, that is correct. So like, again, linear independence seems easy, right? So I can say, so turns out it's easy to show that they're linearly independent. How? It's like pretty much the same deal. So like, assume there's some lambda I vi equals to 0, and then you can just dot it once again. And you're fixing j for here. So this is the it runs from I equals 1 to m, and then you sort of get something like, so the only place where you get a 0 is when you dot it with itself, right? So you get something like lambda 1 plus lambda 2 plus up till lambda j minus 1 plus lambda j plus 1 plus up till lambda n equals to 0. So adding back, you get summation of lambda 1 plus, so summation of lambda I equals to 1 to m. You get this, just a second. Yeah. So summation of lambda, you get I equals to 1 to m equals to lambda I. And so this means that where your like lambda j was sort of different, I'm sorry, lambda, where your like lambda j, the j was constant. So like you can do this for all other terms. So this would give you something like lambda 1 equals to lambda 2 equals to lambda n. Not lambda n, lambda m, and then from there it's easy to show that they can't obviously equal to 1, and hence they will have to equal to 0. Because if they equal to 1, then you get something like, I think you get here m equals to 1. Wait just a second. Okay, so actually, wait, I think I messed up the proofs. Oh no. Oh, okay. So assume like they were linearly independent. So if like it's supposed to be n. Right. Sorry. So like if like m greater than equal to n was like possible, then you could find. Then they would not have been linearly independent, and you could. Wait, just a second. I got confused. Wait a second. Oh, okay. So this, I think. Okay, just I think. Wait, I sort of like mixed the. Num. Okay, so sorry about this. I sort of mixed the argument. So it turns, so you can actually prove that they are linearly independent, but before that you have to sort of drop the dimension by 1. That is important. This is what I was sort of missing here. So like so we want to prove that m is at most n minus 1, right? So now let's say we sort of just prove that, let's say we prove that like just VIs are linearly independent. Then that would just prove M is at most N, right? So we need to drop the dimension by 1. So dimension by 1. So in other words, we sort of need to show that VIs can't span all of F2N. So let us try to first prove this, and then we will try to prove if they are linearly independent. So can you tell me why, like how we can sort of show this? So first, I'm trying to prove that even if they are linearly independent, they cannot span the entire vector space. And then I will prove they are linearly independent. So can you tell me why this is true? So I'll write the conditions on again. Vi dot Vi is 0 and Vi dot Vj is 1. So like, what can you say about this condition? So what does the condition Vi dot Vi? So let's say your vector, so let's say a vector V, which is just given by V1, V2. Okay, this is bad notation. Suppose you have a vector X in F2N, right? Such that like X is X1, X2 up till Xn, right? And suppose I'm saying X equals to, I'm saying X dot X equals to 0, right? Then what does that mean? So this basically means that X1 squared plus up till Xn squared is 0 mod 2, obviously. And but like X1, like all the Xi's are either 0 or 1, right? So Xi squared is actually just Xi. So this basically tells you that X1 plus X2 plus up till Xn is 0 mod 2, right? So now just consider the subspace. Consider the subspace U given by like all vectors in F2N such that summation of the Xi's is equal to 0. So I know that this is also the exact subspace of vectors X such that X dot X equals to 0, right? So now I know all the VI's. So call this I call this U. So now I know all the VI's belong to U, right? And this actually means that the span of all the VI's must also belong to U. Sorry. But then I know that obviously U is not the entire F2N, right? For example, like if you have just consider the vector with a 1 in a first place and everywhere else it's 0, in the sum of the coordinates is 1, which is obviously not 0, and hence that vector is not in this subspace U. So this subspace U is obviously not F2N. So that implies that dimension of U is at most n minus 1. Okay. So now we have sort of dropped the dimension by 1, and now we will try to prove that it's not possible to sort of say that, so it's not possible for them to be linearly independent if M is greater than N. So now assume, if possible, M is greater than equal to N. So we wanted to prove M at most N minus 1, we assume the opposite. Then consider vectors. V1 up till Vn, and there are some remaining ones which I don't really care about. And suppose that, so these are n vectors, right? So since there are n vectors in a subspace of dimension up to, at most n minus 1, so then they are actually linearly dependent, right? So this means that there exists lambda i's such that summation lambda I Vi equals to 0, right? But now again we dot it with Vi. So let's say I dot it with Vj. So this gives you summation I equals to 1 to n Vi dot Vj equals to 0. So this basically gives you I not equal to j lambda I equals to 0. In other words, it gives you I equals to 1 to n. The sum of all the lambda i's is equal to lambda j. But since j was like arbitrary, you can actually say lambda1 equals to lambda2 and so on up to lambda n. But now here's the catch. So suppose all of them were equal to 1, right? So if the lambdas were equal to 1, then when you write this equation tells you that 1 plus 1 n times equals to 1. But n was even. So this means that this is basically just 0. So this is a contradiction. So this is a sort of a specialty of this proof. Like this is considerably harder than the first problem, because here you cannot directly show that n is equal to. So here you cannot directly show that all the vectors are actually linearly independent. So the problem with showing they're linearly independent like right away. So is that it only gives you m at most n, but we need m at most n minus 1. So is there a question with this proof, like any doubts regarding this proof? I'll just go over it quickly. So we again so here the idea was like you have vi dot vi is 0 and vi dot vj is 1, and we want to prove for that for the n even case, I want to show that the maximum is at most n minus 1. So now, so the idea is like before trying to prove linearly independent. So now if I just prove linearly independent, it will just give me m at most n, but I need something stronger. I need m at most n minus 1. So we need to drop the dimension by 1 somehow. And we do that by showing that the VIs can't span all of the vector space. And we do that by like looking at like just consider the subspace U given by this thing like summation xi equals to 0, then I know that this is exactly the subspace of all those vectors we satisfied dotted with themselves equals to 1, dotted with themselves equals to 0, right? So all the VIs belong in this subspace, and hence the span does as well, and hence the dimension is at most of the span of those guys is at most n minus 1. And now we can prove linear independence. If m was at least n, then you have n guys in a subspace of dimension at most n minus 1. So they are linearly independent, but then that gives you a contradiction. So any questions with this proof and any ideas for n odd case?
Can you scroll up a little bit? Why were we able to assume that V1 through Vn are linearly independent?
Can you repeat? Hello.
Yeah, can you hear me?
Hello. Am I audible?
Yes, you are.
Okay. Can you type your question in chat? Actually, the voice is really breaking.
Okay.
Probably my internet. So meanwhile, if someone wants to suggest how do you do it for n odd? So it's kind of stupid, but so n even was sort of the main question. Ideas for. No, we actually did not assume linearly independent. So like we sort of showed that you cannot have m at least n. So what happens is like when you have m at least n, right? So you basically have like at least n guys in vectors in a subspace of dimension n minus 1, right? So they have to be linearly dependent. Like such vectors lambda have to exist. But then after doing the math, you see that the lambda should actually equal to 0, which basically contradicts, right? If they were all, so we prove that they are all have to be equal, and like if they are all equal to 1, then you see that there is a parity problem. So that's the idea. Does that make sense? So like,
by the way, just to confirm, you showed dimension is less than or equal to n minus 1 because the set 1, 1, where everything is 1 is not possible, right? in an even
Yeah,
thing.
like something like even 1,0,0 is not possible.
Yeah, okay.
No, they do not have to be linearly independent. It's the other way down. They have to be linearly dependent, because if you have at least n vectors in a subspace of dimension n minus 1, then they have to be linearly dependent, because like any basis can have a size of at most n minus 1. Right?
Right. So where is the contradiction here?
But the contradiction is like, so we assume that they are linearly dependent, which means that there are some vectors lambda such that all lambda does not equal to 0, right? And then we prove that, so first we prove that all the lambdas will actually have to be equal. They are not all 0, they will have to be like all 1, right? Because you're working in F2N. And so,
I see. That makes sense. So just to
okay. So like
clarify,
here, if they were all equal to 1, okay. Are you saying anything?
yeah, just to clarify, what we did was
Hello.
first assume that, can you hear me?
Okay, I'll just like go over the proof once again. So like, just a second, so recap. So first we proved that the span of the VIs, the dimension of the span of the VIs is at most n minus 1. So now if M is at least n, then that is n guys in a vector space of dimension n minus, at most n minus 1. So they are linearly independent. Sorry, linearly dependent. So there exists lambda I, all not 0. And the other choice for lambda is really 1, because you're working in F2N, such that summation lambda I Vi equals to 0. But then we showed that all the lambda i's are actually equal to the same thing. And if the value is 1, then you have a contradiction. So they all have to be 0, right? So that was the idea. So for n odd, it's kind of stupid. What you do is you add in a ghost member. So what does that mean? You like, instead of seeing the CIs as subsets of 1 to n, you see them as subsets of 1 to n plus 1. And the n plus 1th member never goes to any club. Then you would have m at most n plus 1 minus 1, because n plus 1 is 0. So does that make sense? So this is kind of sort of stupid, because like, sorry, the real problem was really doing it for the even case. And for the odd case, you just take, so you sort of artificially increase the size of the total number of elements by 1, and that is even, so it works out. So any questions regarding this? Okay, let's do another problem. So let yeah, A1, A2. So let A1, A2 of till an plus 1 be two subsets of be n plus 1 subsets of 1 to n. Prove that there exists disjoint sets I comma j belongs to 1 to up till n, such that union of I belongs to I, ai, and ij non-empty equals to j belongs to j, aj. So the problem is basically you have n plus 1 subsets, a1 up till an, right? And prove that there exists some disjoint indexing subsets of 1 to n, such that like the union of some of those guys is equal to the union of those of the other guys. So something like you will end up having something like a2 union a3 union a5 equals to a6 union a7 or something like that. In that case, your I is 2, 3, 5 and your j is 6, 7. Just to make the problem statement clear. So is the problem statement clear to everyone? Any
Yes.
questions? Okay. So now I
Shouldn't
will.
it be like I comma j are subsets of 1 to so until n plus 1? Because then we are not using the set a n plus 1 basically, right?
All right. Sorry. Yeah. Sorry for that. That was a typo. Yes. Sorry. So yeah. So how do you go about this problem? So once again, we will sort of think of use a difficult. So think of AIs as vectors in F2 and call them VIs. So that this is n plus 1 vectors in F2n, right? So they are obviously linearly dependent. So this means that there exists constants lambda I, lambda j, sorry. So lambda I equals 1 to n plus 1 such that summation lambda I times vi, this is not a dot product. So I equals 1 to n plus 1 is equal to 0. But what next? Like, okay, so we got till here. I know that there are n plus 1 vectors in F2n, so they must be linearly dependent. And I know that hence you can write something like lambda I vi equals to 0 summation. So like what next?
Wait, so since 1 is equivalent to -1 in F2,
Yeah.
we can sort of like, uh, unless like only, yeah. And none of the VIs is all zeros because it's not
Yes.
equal to. So, like, they're like at least out of the lambda is at least 2 are non-zero. And since 1 is
Okay.
equivalent to -1, we can like, yeah.
No, I don't actually follow the argument. Can you repeat?
Oh, okay. So let's say like we have like some index set like k, so that for
Okay.
summation v small k, where k is in like the our index set is equal to 0. So lambda i's are either 0 or 1,
Oh, so
right?
basically all those.
Yeah.
Yeah, for in F2n, yes. So yeah.
So there are some vectors which add up to 0, and like all of those vectors, like the cardinality of the number of such vectors is at least 2. It cannot be 1 because the all 0 vector doesn't belong, like is not a valid subset. Uh,
Yes.
and then since 1 is equivalent to -1, we can take some of the vectors to the other side, and then yeah, then sum of like some vectors will be equal to some of the other vectors.
So you're basically saying something like v1 plus v2 equals to v3 plus v4, let's say. Then you take I equals to 1 comma 2 and j equals to 3 comma 4. Is that what you're trying to say?
I think so, yes.
Okay, so there is a problem with this. So actually what happens is, like, suppose you have two sets A and B in F2n, right? So just consider the vector sum of A and B. So this is actually
But
A del B, where this is the symmetric difference. So this does
yeah,
not work actually. So looks like F2n does not work. So like what's so okay, so this is kind of this is probably very hard to motivate. I like when I read the solution 5.7, I did not actually understand what the real motivation was. So the idea
Wait,
is
can I say an idea?
yeah, go ahead.
So is it something like you assign a vector to each number? So like to number 1, you assign the vector like n plus 1 length vector such that AI is 1 if it's in set AI.
So oh, so you have n plus 1 vector. So you have n vectors, each for a element. Okay.
Yeah,
V1,
but
V2 until Vn. But these are in some vector space of dimension n plus 1.
yeah,
Then how does that does not help with anything, right? Because you can't
yeah, I
take any.
realize it. Yeah, because they can be, yeah, fine.
Yeah, so you have two less vectors. So the idea is you will consider them as vectors as in Rn. You still put 1 and 0 wherever they are, like wherever there is an element or not an element. But now when we write I equals to 1 and plus 1 lambda I phi equals to 0, lambda is a not just equal to 0 comma 1. This restriction no longer valid. So no longer valid. So like, how do you go about this now? So now this is very sort of hard to motivate. So what you do is like, you sort of need union AI, you need this condition to hold, right? So think of like, so the idea is sort of this. So uh, let I denote the set of okay, let I denote the set of alpha i's, lambda i's of lambda i's such that lambda I greater than 0. No, sorry, just the i's. Sorry. So suppose I denote the set of i's such that lambda is greater than 0, and let j denote the set of j's such that lambda j is less than 0. Then the claim is that my actual sets are actually just like I and j as written here. So claim I and j work. So now why is this true? So proof goes like, so suppose there is some vector, not vector, sorry, let's say there is some k in union of in the union of the AIs, but not in the union of the AJs. Right. So now you know that there exists some I such that VI's kth coordinate is not 0. So this is basically, I'm just saying like EK is the kth basis vector, kth standard basis vector. So so you don't need to think about this like this. I don't know why I wrote this. So like EK is basically, you have a bunch of zeros and you have a 1 in the kth position, and then you have zeros again. Kth coordinate of Vi for some I in I is not equal to 0. In fact, it is greater than 0. Right. Oh, sorry, it's not. Can I say it's greater than 0? No, you cannot say it's greater than 0. I mean, sorry, that was, sorry, I was clowning. That is just equal to 1. So you can say that for some I belongs to I, the kth coordinate of Vi is actually just equal to 1, right? But now consider the contribution of this coordinate in summation lambda I Vi, right? So now consider the kth coordinate of this sum. So I know that the kth coordinate for this is at least lambda I Vi, right? It is 0 for the guys for which it is at least 0 for the guys which has their lambda is 0, and then there might be some guys with lambda j which is like negative, but like I know that there are no AJs containing k, right? So what that means that the kth coordinate of all the AJs is 0. So which means that there is basically no negative contribution to the term, to the sum lambda I Fi in the kth coordinate. So the kth coordinate is always at least lambda I Vi. In particular, it can never be 0. So this is a contradiction. So this way we prove that union of I belongs to I, AI equals to union J belongs to J, AJ. So any questions with the proof? So this was a sort of a different idea. So we realized that working in F2N is not enough, because here their vector addition means something different. It means like taking the symmetric sums. But when you think of them as vectors in Rn, then my constants are much more flexible, and you can actually say something about them. So you take the set where for which the constants are greater than 0 in one partition, and the other one you take the ones which have like less than 0. So now the claim is that those are the working subset, working indexing subsets. Why? Because you realize that suppose let's say some element k is in the union of the ai's but not in the aj's, then there will be some element, some set ai such that its kth coordinate is, it contains the element k. In particular, the vi has kth coordinate non-zero. But then when you consider the contribution in summation lambda in vi, there is no negative contribution, because the only negative contribution could have come from the from the lambda j's, but you know that the kth coordinate there is just 0 because none of the aj's contain k. So is the proof for this problem clear? I'll move on to the next problem, which is sort of related.
I think there was a typo in the first line. Can you?
Oh, yeah. Here.
In the first line of the proof, yeah, it should be no, a little bit down, like proof, like the actual proof.
Okay. Yeah, here. Hello.
Yeah, you've written suppose K belongs to union of all AI where I belongs to J. I think it should be I belongs to I.
Oh yeah. Oops, sorry. Okay. Yeah, sorry. But K doesn't belong to. Yeah, right. Thanks. Okay, so the next problem is sort of a related problem. So let A1, A2 up till AM be sets of, just a second. Yeah, let A1 up till AM be subsets of 1 to n. So this notation is used for writing 1 to up till the set 1 to up till n. Find minimum n such that you can always find, also AIs are not are non-empty. Always find I comma j subsets of n plus m, subsets of m such that I and j are not empty and disjoint. Condition, and the following condition is satisfied. One is I belongs to I, AI equals to j belongs to j, aj, and I belongs to I. Sorry, this is not a union. And intersection I belongs to I, AI equals to intersection j belongs to j, aj. So the problem is basically saying that you have, let's say, m subsets now of 1 to n. Find the minimum value of m such that you can find the similar like ij as in the previous problem, non-empty disjoint, such that the unions are the same as well as the intersections are the same. So question, does n plus 1 work? So can someone tell, so like, can you think of a construction or a non-construction for n plus 1? So any ideas? Like, does n plus 1, do you think n plus 1 will satisfy?
Guess is no, I'm thinking of a construction.
Come again?
Like I was guessing that it's no, but I was thinking of a construction, like for which it fails.
Yes. Okay, so I'll just mention the construction, not very hard to come up with. Consider the subsets 1, 2, up till n, and then the subset 1, 2, up till n. So this shows that n plus 1 fails. So convince yourself this is true, not very hard. Because when you consider the, so like, so like if your this set is not in the union, then it was obviously going to fail. So it will have to be somewhere. And yes, it's easy to see that this fails. So the next best thing we can do is n plus 2. So now it turns out that n plus 2 does work. Right. So now how do you go about proving this? So now merely the using the fact that n plus 2 vectors are not enough, n plus 2 vectors are linearly dependent is not going to be enough. It's not going to suffice. So what do you do? So using n plus 2 vectors linearly not enough. So think about it. In the previous problem, we needed so just a second. So previous problem, we needed summation, union of I belongs to I, AI equals J belongs to J, AJ, right? So what we did was we had summation lambda I VI equals to 0, and we picked I to be those I such that lambda I is greater than 0, and J to be those I's, J such that lambda J is greater than 0. So now what can you do? Like, so like, okay, so think about it like this. First of all, only linearly independence is not enough. You need some other condition. Otherwise, the problem would have held for n plus 1 as well. So you need another equation of sorts to distinguish n plus 1 from n plus 2, right? So now I need also here, I also need intersection. So intersection of, okay, so let me just write this. Right? So this is equivalent to saying union of I belongs to I, AI complement equals to union of J belongs to J, AJ complement, right? So now again, so sort of think about it like this. You wanted to have like, so if you were just sort of asked to find some I and J such that the union of AI complement and AJ complement are like the unions the same. So what you would do is like you would sort of try to so let's say vi dash are the vectors for the AI complements, right? So you'd want something like summation lambda I vi dash equals to 0, and take I equals to the set of I such that lambda is greater than 0, and J equals to the set of J such that lambda J is less than 0. So you sort of need to do both of these simultaneously. Then how do you do it? So now what is vi dash in terms of vi? Is it just 1 minus vi because the AIs are complements? Sorry, because the AIC is like the complement of AI, right? It exactly avoids those elements that AI has and has the other ones instead, right? So you need something like summation lambda I 1 minus vi equals to 0, right? And you sort of need the same lambda i's to work for my VIs as well. So like this sort of wishful thinking. Sorry, just a second. Wishfully thinking. I need lambda i's to work the same lambda i's to work for VIs for the VIs as well. So I need one, that is summation lambda I vi equals to 0, and two, summation lambda I 1 minus vi times 0. So this basically tells me that I also need the lambda i's to be 0. So the sum of the lambda i's to be 0. So now think about this. So consider reals lambda I such that the following n+1 equations are satisfied. So here the lambda i's go from I equals 1 to n+2, obviously. One is like summation lambda I vi equals to 0. So this gives me n+1 equations every coordinate. Sorry, so this gives me n equations for every coordinate, one for each coordinate. And the second equation I choose is summation lambda I equals to 0. So this is n+1 equations in n+2 variables. So has a non-trivial solution for sure. So now take I equals to the i's such that lambda is greater than 0 and j equals to those guys which have lambda j less than 0. So, and as before, the I and j work.
Okay, but if you had like
So,
n+1
anyone has
equations,
any question? Go ahead.
yeah, if you had n+1 equations in n+1 variables, then also you'll have a non-trivial solution always, right?
Not necessarily. Not necessarily. What if your matrix is not inverted?
Oh,
Right. So yeah, so this works basically because you have lesser number of equations and variables. So obviously a non-trivial solution must exist, but you cannot. That is kind of why the n+1 case fails, right? Because you can choose your matrix to be to have like no determine 0. Sorry. So I will just go over the proof of this once again. So like in the previous problem, I would still like to have something like lambda if I equals to 0 and like to choose the I set to be lambda I greater than 0 and the j set to be lambda j less than 0. So this is right. But on the flip side, I also need something like the intersections the same. So the intersections can be interpreted as like union of the AIs, union of the complements, right? So now suppose your VIs are the vectors for the complements of can you explain why n+1 doesn't work? Okay, I'll just do it. Just a second. So you would want something. So first of all, you would want something like lambda vi dash equals to 0, right? And take like you. So for having something like union of AIC in for the I indexing subset to be for union of the j guys, you would need the same thing. You would like want to have some lambda I dash some lambda I such that the sum is 0, and you like take the guys positive in one partition and the negative guys in the different partition. But like you sort of need these two conditions to hold at once, right? In other words, you sort of need these two equations to hold at once. This is sort of wishfully thinking, and I know that these are n+1 variables in n+2 equations, n+1 equations in n+2 variables. So it does have a non-trivial solution. So I just take that tuple lambda1 up to lambda n+2, which will give me a result. So why does n fail? So someone asked, why does n+1 fail? So that's because like this is the construction for n+1. So it's not very hard to understand why it fails. So this one. So you consider the sets 1 to n and consider this set 1 and consider the entire set n. So that is n+1 subset. So n singletons and 1 is like the complete set. So I know that so like if let's say call this set the n+1 set, right? So for this set, if the lambda value is like not is equal to 0, then you know that this is going to fail, right? So this is sort of basically equivalent to taking n vectors, and this reduces to the previous case. Yeah, it's not very hard to figure out. Okay, so okay, so that concludes this problem. Okay, I'll sort of show a new problem. Probably won't have time for the Hamilton basis problem. So let's sort of turn to some questions of geometric flavor. So geometric flavored questions. So first question is like, this is going to be about set of lines such that every two of them have the same angle between them. So how many lines through origin in R2 can you draw such that the angle between them is always the same? What is the maximum number of lines you can draw in R2 such that the angle between any two of them is the same thing? Anyone wants to answer? So why I want all the lines passing through O? Sorry, did not write this properly. So one line mention this. Want lines passing through origin such that I do not want infinitely many parallel lines, families of parallel lines, and so on.
Are we looking at the directed angle? As in, like, can we do 60, 60, 60
Oh.
I mean, sorry, 120,
Yeah,
120.
that. I mean, yeah, it does not. So let's say just it's 60 or minus 60 or something like that. Yeah, I think. I mean, the directed angle. Yeah, that's fine. I mean, the 60, 60, 60 is the only thing you can actually do.
Yeah.
So the answer is 3. How you take? Okay, that was a very poor drawing. I mean, 60 degrees with respect to both axes. I think that's what you meant. 120, 120, right? So now, yeah. So how do you answer this problem for R3? So what about R3? So yeah, again, you are looking at lines passing through the origin such that they have the same angle between any two of them.
Is it still 3?
Okay, so let's say you consider like a regular tetrahedron, right?
Oh, you can
Which
take 8 lines, I think.
What? How many?
You can take 8, right?
How?
Oh, sorry. I was taking segments. I was like positive x, negative x. That just counts as a single line. Sorry.
So like in R3, if you just take something like 3 pairwise perpendicular lines x, y, z axis, that's 3, right? So 3 is easy. So just a second. X, Y, Z axis gives you 3. So can we do 4? Yes, I'll just like mention it. The proof is kind of long for this. So we can do 4. So consider regular tetrahedron with center at O. So consider the regular tetrahedron to be named ABCD. Then the lines OA, OB, OC, OD are okay. So it turns out that the maximum value is actually 6. How do you get 6? Is like consider an icosahedron. So this is kind of non-obvious. So this is
What is an
12 vertices.
icosahedron?
So it's like, okay, I'll just show you a figure. Just give me like 1 second. I should have taken. Just a second. Okay. Yeah, so this is an icosahedron. Oops. So this is obviously like it has 12 vertices, and you take lines between opposite sides. Sorry, opposite vertices. So consider a regular icosahedron. So that gives you 12. So like, do you sort of see a pattern? Okay, this is probably not very hard to guess. So for R2, you have 3. You have, for R3, you have 6. Can you maybe guess a pattern for Aryan? Okay, so this is, okay, I'll just tell you. Yeah, go ahead.
N into n minus 1. Oh, wait, no.
3 into n minus
No,
1.
it's actually, so it's actually just n times n plus 1. So this is, yeah, so this is n plus 1 choose 2. So now we will try to prove this theorem. So theorem or problem, whatever, there are at most n plus 1. Actually, let's work in RT lines in RT such that angle between any two is same. So yeah, so now proof. So let's say my angles, so let's say my lines are L1 up till LM. I want to prove, want to show M at most D plus 1 choose 2. Okay, so let the common angle be phi. Right. Let Vi denote unit vector in the direction of Li. So obviously you are considering these vectors in RT, right? So then what can you say about Vi in, dot Vj? So this is obviously 1 if I equals to j, because the Vi is a unit vectors. And if they are not equal, I know that the angle is like, you know, from physics or something, like it's Vi dot Vj cos squared, sorry, not cos, but just cos phi, right? The cos of plus minus phi, because depends on what direction you chose the VIs in. So this is cos of plus minus phi. Wait a second. Sorry, that was wrong. Cos of phi or pi minus phi. So it's actually plus minus cos of phi if I not equal to j. So depending on how you choose, depending on orientation, the angle might be phi or pi minus phi, right? Cool. Okay. So now how do you, sorry, I don't mean to do that. So how do you go about this? So you are given m vectors in RT such that this condition is satisfied, right? Satisfying star. And you want to show m at most t plus 1 choose 2. So first of all, obviously, if you are just trying to work in like RD, that seems like not sufficient. Like it seems so like any sort of basic linear independence argument is not going to work because your dimension in RD is too low. So what we sort of try to do is we will consider the vector VI. So think of VIs as column vectors. So this is question. So consider VIs as like column vectors. So if my VI is a, just a second. So if my VI is a d cross 1 vector, then my Vi transpose is a 1 cross D vector. So Vi transpose is a D cross D matrix. Right. So we are
How
given.
is Vi defined? Like the unit vector I see, but like how do you define it as a vector?
Oh, it's
I
just you
mean,
consider a unit vector along the direction of Li, along like the direction of Li.
so like what's the D cross one thing? Like in like
Okay, so suppose you have like, okay, I'll just give you an example. So suppose you have something like your line is passing from 0, 0, 0 to like 1, 2, 3, 4, 5. Then your vector is just 1, 2, 3, 4, 5. Does that make sense?
yeah.
And you like sort of, I mean, you actually think of it as a column vector. So you think of it as 1, 2, 3, 4, 5. You think of it as a column vector rather than a row vector. Okay, so we are going to look at Vi transpose. So something uncanny about this is like this matrix is symmetric. Why? Because when you take the transpose, it gives you this. So when you take like the transpose, you sort of flip. So this is how you take transpose. So this gives you VI. So in other words, VI is symmetric. So now what can you say about space of symmetric functions, symmetric matrices in R T cross T? What can you say about vector space of D cross D symmetric matrices?
Like it should have dimension D square, like D choose 2. Wait. Yeah, D choose 2. So wait,
Why,
is it D
why
choose
is
2?
it D choose 2?
Oh, sorry, it's D plus
Why do you think?
1 into D by 2. D plus 1 choose 2. Because basically, like you consider the diagonal and
Right.
all the elements below the diagonal. Only those are being affected. Like if you consider those, you do not lose on information, right? Because
Yes.
the diagonals below, or the elements
Yes, right.
below give the information about above.
Because the upper guys are completely determined by the lower guys. So yeah, so that is kind of the idea. So obviously, so if you're, it's not clear why it's a vector space, you first convince yourselves it's a vector space. So now what's dimension? So call this vector space to be U, right? So what is dimension of U? The idea is like when you are specifying symmetric matrices, you need to specify all the guys along the main diagonal and then all the guys along the sort of the smaller diagonal. So as long as you specify the lower half, the upper half is sort of fixed, because for a symmetric matrix, you have like AI is equals to AJI. So this is exactly equal to D plus D minus 1 plus D minus 2 and so on up till 1, which is D plus 1 choose 2. So now this is how like, so now we know that, so this subspace has dimension D plus 1 choose 2. This subspace of R D cross D. So now I want to prove that VI when viewed as elements of U are linearly independent. So this would show that M is at most D plus 1 choose 2. So how do you go about this? It's like it's pretty similar. So you have something like summation. Just a second. So you have something like summation. So assume not linearly independent.
I have a question.
So there exists. Come again?
I have a question. So if we consider the vector space of all
Can you
D
repeat?
by matrices,
I cannot understand you. Can you repeat what you said?
yes, am I audible now?
Yeah. Ask the question.
So if we consider the vector space of all D by D matrices,
All D by D symmetric matrices. So that
no,
was important.
we just consider the
Okay,
space
okay.
of like all matrices, then that has
Okay.
dimension D squared, right? Okay, never mind. I answered my own question. Sorry.
Yeah, so the dimension of all D cross D matrices is D squared, yes. Yeah, so the idea is like you want to sort of redefine the subspace the vectors belong in as much as possible so that you can actually use dimension argument. So that's the entire point. So you understand it's symmetric and that's sufficient, like because the symmetric space will have D plus 1 choose 2 as its dimension. So there exists some vectors. So coming back to the linear independence argument, assume they're not linearly independent, there exist some vectors lambda I, not all 0, such that summation I equals 1 to m lambda I vi equals to 0. Sorry, lambda I vi vit equals to 0. So now what I will do is I will left multiply with lambda j vjt and right multiply with vj. So this gives equals to 0. But now you know that, but note that, so what is vjt dot vi? So what is this value? So first of all, I know that this is a this is a n cross sorry d cross 1 matrix, right? Sorry, 1 cross d matrix, right? And this is a d cross 1 matrix. So what is the number of, like, what can you say about the order of vj transpose vj transpose vi? This not dot.
Is it something we determine in
What can you say about
no. What's the order of a
no you are
matrix?
It will be a constant.
order is in like, yes, like I want, so like m cross n matrix, it's a 1 cross 1 matrix, right? Because you have like 1 cross d and d cross 1, so it's just a constant, so it's actually just equal to vi dot vj. That's the like idea. So vjt vi, when they are multiplied as matrices, this equals to a 1 cross 1 matrix, which is just vi dot vj. So when you are, so call this star star, so star star sort of translates to summation lambda I. So this gives me a vi dot vj and this gives me a vi dot vj. So this gives me vi dot vj whole squared I equals 1 to m equals to 0. So this again gives me lambda j plus I not equal to j lambda I times cos squared phi less than equals to 0. And so this basically means that so you can write it sort of like this: cos squared phi equals to cos squared phi times summation I equals 1 to n lambda I equals to cos squared phi minus lambda j, right? So now you could have chosen lambda to be could have chosen phi to be less than pi by 2, and this imply that all the lambda is are equal to each other. And furthermore, sort of note that next note that in this equation, LHS and RHS will have different signs unless lambda I equals 0. So that is the proof. So you again do the linear independence argument, and when you sort of see like when you try to do it, so yeah, so the linear independence argument is pretty standard of sorts. Like the only sort of catch was noticing like this is true, and then when you try to do it, you get this equation. And here, if so, first of all the lambda is are equal because the angle was chosen to be at most pi by 2, and finally like if they are not all equal to 0, then this guy will be a positive sign or a negative sign depending on the sign of lambda, and this, since this guy is strictly less than 0. So any questions?
How do you motivate using linear algebra in this? Like the statement is purely geometrical. It's not even
So
combinatorial.
yeah, so this is like sort of one class of problems which like, so this is sort of falls under linear algebra methods. This is like kind of the point, like how do I put this? The problems are otherwise geometrically, like combinatorially thinking pretty hard to solve, but when you sort of model it as a linear algebra problem, it is like much easier, much more manageable. So the idea is like, this is obviously you sort of need to have seen some, at least some ways in which you sort of use linear independence results, like the easier ones I showed you before. But for this to hold, like again, you are trying to sort of use a linear independence argument. So like not all linear algebra, so like linear algebra methods in combo does not like start and end at linear independence. That's just like one very basic usage. So for this problem, it's like you sort of try to do it and then you sort of refine it by making the symmetric matrix, by getting the symmetric matrix name, and you proceed like that. So does that answer your question? Probably answer satisfactory answer, but like you kind of need to have seen something like this in advance.
Mhm. Yeah, okay.
So I don't think I have time for anything else. So any questions regarding the overall talk? Please feel free to ask. My handwriting like uh, just went haywire towards the end.
It's very good comparatively.
Thank you. Any questions from the people?
Can you suggest resources for further reading?
Okay, I think I'll just I can you put your question in chat? My internet is pretty bad, I think.
Also, should I stop recording? Oh, okay.
Yeah, yeah, sure. I think so.